Hi, everyone. Thank you very much for being here. And this is the start of an exciting new term. And we are the society that periodically invites Neel for talks. And this is another talk by Neel. And today he'll be talking about an introduction to reinforcement learning, which is an exciting topic in itself. And I'll just plug another talk from the Archimedeans that's happening 4 weeks from now by Susan Murphy, which is on the same topic of reinforcement learning. But that being said, I'll hand over to Neel and hope you enjoy the talk.
Awesome. I feel I should probably add that given what I know of the talk, it's just completely different material to what I'm covering. So if you enjoy this, you should definitely go to that one, because it's about causal inference, and causal inference is lit. Anyway, thank you very much all for coming out so far today. I appreciate it. I'm going to split this talk up into chapters and have like a break in the middle. This is going to be a talk on reinforcement learning. And I'm guessing many of you probably not have actually come across the field before. So reinforcement learning it's an area of computer science and machine learning that's basically the computer science of how decision making works and how you can train programs that make decisions. And we're going to dig into a load of like the techniques and problems in this field and the interesting things that can happen with it. So this is a pretty biologically motivated area. So I think it's first good to think about how do humans learn things and try to take inspiration from this. So I think there are two main categories of how humans learn things. There's direct instruction, so just being told what you should be doing, like by your school, university, parents, or by a random dude pontificating about reinforcement learning. And that's a boring kind of learning. But we also learn by just doing things. Like say, I know that I enjoy Indian food more than I enjoy Chinese food. This isn't something that somebody like taught me. I just tried both and found that I liked one more than the other. And I think that quite a lot of the things people learn, nobody tells us these things. We just go out into the world, explore, do things, and some of the things we do we feel happy about, some of the things we do we feel sad about, and over time we get better and better at doing the things we feel happy about. This has a dark side. Like say, I think a lot of people get pretty addicted to their phones and to social media and Facebook. And nobody taught you you should be addicted to these things. You just started using them, you enjoyed using them, you started using them more, and it's like kept going in a cycle. And this idea is the core of what reinforcement learning is. So we can kind of abstract that out. We do actions, and we get rewards for those actions. Or we get punishments, like the proverbial carrot and the stick. And humans are biologically programmed. When we get these rewards, like this pain and this pleasure, we tend to do more of the things that make us happy and do fewer of the things that make us sad. And the core idea of reinforcement learning is just, how can we abstract this out to machines? How can we get machines that do things, get positive reinforcement for the actions we like, negative reinforcement for the actions we don't like, and learn to take more of the positive actions over time. And the formal framework of this is that we just directly put a number into the program. We call this number the reward. We make it positive for stuff we want it to do more, and negative for stuff we want it to do less. And we tell it, go off and maximize this number. And this is all like a kind of very vague, high-level description, because reinforcement learning is basically just a category of optimization problems. You have an environment, you have actions you can take that get rewards, and the goal is to write a program that can learn how to maximize this reward. And one of the really interesting things about this, and things that make it really different from most of the rest of computer science and machine learning, is that it's about a sequential decision process. I'm not just, I want to train a program which gets reward from its environment and makes like lots and lots of decisions and over time tries to increase the total amount of reward it gets, rather than say a program where I just like give it a picture and it tells me is it a dog or a cat, and it just like does that again and again. Like there's room for things like learning, long-term planning, but also maximizing reward, and we need a program that can learn how to trade off between these two. One example of this might be how to make a self-driving car. So in a standard machine learning programming paradigm, you'd want to explicitly write an algorithm that drives. Like, notice things that are nearby you and don't crash into them. Keep to the speed limit. Keep in your lane. Follow the route the GPS gives you. And you're like explicitly telling it what to do all of the time. And this can work really well. But this can also give things that are kind of brittle. It's fundamentally limited by the knowledge of the person designing the program. And these can get really complicated and convoluted and miss lots of things. And the reinforcement learning way of raising this problem flips it all on its head. We just tell the car what driving counts as good, what driving counts as bad, like not speeding, keeping in the right direction and lane. These all get positive reward. Killing people or crashing into things gets negative reward. You then give it access to sensors, and like all of the information it would need to make decisions, and you let it figure it out. Obviously, we don't actually want cars that crash into things in order to figure out the crashes are bad. So when people actually make self-driving cars and practice with these techniques, we tend to train them in simulation rather than training them in the real world. But the core idea is just you give it enough information to figure out what is and is not a good idea, and then it learns what to do on its own. The key is that it derives strategies, and this is often a lot harder, but also way more interesting because there's so much more room for creativity and for just finding ways to achieve the goals you want. Another key is that it's sequential. So this opens up a few interesting things you wouldn't normally get in a machine learning problem. So one is that information is really valuable. Like if a car is kind of driving down the route it thinks is the best route, but there's another route that it basically never taken, it could try going down that route, and maybe it would take longer. There's some cost, but maybe that route is actually way better than its normal route. And if the car decides to take that weird route, there's a cost in the short term. But if it's a better route, every future time it can take that shortcut. So you need to have programs that can reason about this and understand how valuable information can be. So like, if it doesn't explore, it might just get stuck taking a longer route. But if it kind of only explores, then it's never going to take the best route. And you need to learn how to balance these things. Another interesting challenge that comes up is you need to care about long-term planning. So, for example, if I'm like a kid and I want to maximize my future earnings, often the correct action to do is to go off to university for 3 years, do a load of random stuff, go into debt and earn zero money. But at the end of that, I like get higher earnings. And you need to have a program that can learn how to do things that have short-term costs that are going to have a long-term payoff. The way we formalize this is that we tell the program to maximize total reward, rather than just like doing the thing that feels optimal in the moment. Often we discount the reward. So say we multiply a reward that's 100 time steps into the future by like some discount factor like 0.999 to the power of 100. This is a bit of a hack. I don't think it's that interesting, so I'm not going to go into it in too much detail. But if you actually look into the formalisms of reinforcement learning, they often do this. Partially just nice because it means that the sums can't be infinite. And so one of the reasons I find reinforcement learning really interesting is that it lies at the intersection of lots and lots of different fields. Like you have engineers who care about how to make systems that do things well, like say how to make a data center that can optimally call itself. You've got economists who are thinking about how can people make decisions about how to spend their money and allocate resources. You've got neuroscientists who are looking at how things learn. You've got mathematicians who are trying to like calculate optimal decision-making processes. And reinforcement learning kind of lies at the intersection of all of these fields. If you'll forgive the overly grandiose diagram. And the other thing that's really exciting about reinforcement learning is that it actually works. So this is a random noodle that some people at DeepMind trained using reinforcement learning to learn how to do parkour and in a simulation. And like, I'm really impressed by this. I didn't think this would be possible when I was first learning about reinforcement learning. And there's going to be way more of cool GIFs of people getting programs to do cool things throughout this talk. So now I'm going to try to like set out some terminology and address common confusions to frame things well. So the right way to think about reinforcement learning is that it's a paradigm. It's a class of optimization problems rather than a solution method. There are lots of different ways of solving reinforcement learning problems. This is in comparison to, say, supervised learning, which is you give a program a bunch of example inputs and outputs to a function, and you tell it, learn what that function is. But there are lots of different ways of solving a supervised learning problem. This is a different kind of thing to deep learning, or things done with neural networks, where neural networks are like a tool. They're a specific solution method that people use to solve things and to approximate things. I think this is worth clarifying because people talk a lot about deep reinforcement learning. I'm often going to abbreviate reinforcement learning as RL because life is too short. And this is using the tool of neural networks and deep learning to solve the problems of reinforcement learning. And this is where a lot of the really interesting progress in the last couple of years has come from. Like people learning how to do things like play Atari games well, or play StarCraft, or play Go better than human levels. So now I'm going to define some more key terms that I'm going to use throughout. So, and I'm going to try to analyze the example of training a reinforcement learning agent to play chess. There's almost certainly jargon that I'm going to actually use without having to find. Please interrupt me if I do this. This is my bad. Jargon is bad. But these words are really important. So the first key thing is the idea of the state. This is like some information that captures everything important about the world. Like in chess, this would be the chessboard, or maybe the chessboard plus a bit of information like have they moved the king before, or have they castled? Like everything you'd need to know in order to figure out what the world will look like from here. Then there are actions. So these are the things the agent can or cannot do. Like a chess playing agent can like move its pieces, and these are the ways the agent can affect the world. There's a reward. So every time an agent takes an action, it gets given back a number saying like, how well did you do? This isn't super interesting in the case of chess, because in chess you kind of only really care if you win or lose. You get 0 for each move, and then you get +1 at the end if you win, -1 if you lose, maybe 0 if you draw. A better example of a more continuous reward process might be, say, this thing called cart pull, where you train an agent to balance a pull on top of a cart, where you can give a reward that, say, how close is the angle of the pole to the vertical? And this is something it can get at every time step, and it's trying to just like keep the pole balanced. And then finally, we have value, which is the total reward over like the kind of lifespan of the program. And this is the thing that's actually optimizing. you only really care about reward in that it informs the value. So this is a useful picture to have in your head. You have the agent. The agent is separate from the world. The world tells the agent what is the current state of the world and what was your reward. And then the agent says, I take an action, gives it to the world, and then the world gives it a new state and a new reward. And the agent just like keeps doing this either until infinity or until the game ends. So why is reinforcement learning useful? Like, why do we care about this? So a lot of the really interesting progress has come from basically playing games. In the last few years, people have learned how to play Atari games, like old school video games, really well. People have learned how to play Go beyond human level, which was a really big deal because Go is hard, and I'm going to talk more about why that was a big deal later. People have learned how to play really complicated, messy, imperfect innovation games like StarCraft and Dota. I think that these are generally, I don't think the ability to play games is that intrinsically interesting. I think it's interesting because often the techniques used to succeed at games can be generalized. So a few examples of actually useful things that we can do with reinforcement learning, like making self-driving cars, making recommender systems, like the thing that recommends songs to you on Spotify or the next video on YouTube. Though that has problems, which I'll touch on later. A surprisingly interesting application is that Google uses reinforcement learning to crawl its data centers. And this sounds really boring, but Google is massive, and Google spends a ridiculous amount of money calling its data centers. And by using reinforcement learning well, they managed to lower costs by about 40%, which is actually kind of a big deal. And finally, I think ultimately reinforcement learning is a pretty young field that's growing pretty fast. And so I think the main reason it's interesting is that the potential for what it could achieve in the future just seems really big. Like, people hype up a lot the idea of artificial general intelligence, making programs that are as smart as humans. I think it's really hard to forecast when this might happen or if it would be possible, though I personally think it's something I'm pretty interested and concerned about. And it seems pretty likely that anything which is similar capability to humans is going to be making like decisions in sequence over time, and the core techniques you need to solve that kind of problem are reinforcement. So I want to talk a bit about why reinforcement learning is hard, because understanding why a problem is difficult is often useful framing when we're thinking about how we actually solve it, because it can focus you on what bits of the solution are interesting and insightful and which are just like boring BS. So a surprisingly difficult part is just describing what the problem is. Like, the space of all possible strategies is exceptionally big, and you kind of need some way to parameterize it and some way to break it down without making it so broken down that you miss out on the best strategies. You need a way to capture the thing we would like the agent to do in this simple numerical function of a reward. These are both difficult problems, though most reinforcement learning techniques don't really focus on them that much, and they're taken as given. But a lot of work should go into getting those right. A lot of challenges come from making decisions in sequence. As I mentioned earlier, you need to think about trading off information against like getting value. You need to think about long-term planning. Generally, you need to understand the environment you're in, and that often takes a lot of data. One of the reasons that there's so much progress in games is that games you can simulate pretty cheaply and get a lot of data, and you really can't if you're trying to figure out, say, how to train a robot to walk, and you can't simulate that well. So here's a graph of a bunch of different systems DeepMind made to solve Atari games. And so 100% is human level, and this is the number of million frames it took. And a million frames is about 4.5 hours of human play. And so this thing, which is the best, took about 18 million frames to rival human play, which is about 320 hours per game, and these are games that humans can often pick up in like an hour or two tops. Like there's a lot of room to like think about how to use data efficiently and just figure out how to solve problems in a way that needs less data, because it's one of the biggest constraints. A few points on how to frame things. So this is not a maths talk. There is a lot of theory, maths, and theoretical CS behind reinforcement learning, which I'm going to talk about a bit. But a lot of the solutions are very approximate. They work sometimes, they don't work other times. A lot of the theory is extremely general, but the things we actually care about are extremely specific. And there's a lot of work that goes into tailoring it to specific situations. So don't expect me to like spend ages proving things. Another warning is I think reinforcement learning is really interesting. And hopefully some of you will be inspired by this talk, go out and try it for yourself. But it's also kind of hard, and we don't quite understand why it works yet. And there are a lot of dire warnings from people in the field about just things take more effort than you think they should. If you run a program with a different random seed, then sometimes it just stops working, and we don't really get why, and it's kind of concerning. I think it's really interesting, but I think people should go into this warned. So to recap the important points in there, reinforcement learning is a class optimization problem that is about how to solve sequential decision-making problems with a lot of different ways of solving things. The key is that it receives information that tells it how good an action was, rather than information about what actions it should take, or what strategies it should follow. And the key problems to think about are how to specify things and solve the problem, how to think about information and long-term planning. And one of the reasons that I think reinforcement learning is really interesting, that I'm going to touch on throughout this talk, is that thinking about RL can teach us how we can make decisions better, because this is fundamentally the science of how to make programs that can make decisions. Sorry, that introduction probably went on for too long, so I'm going to try to speed up a bit throughout the rest of the talk. So the first thing I want to think about is this thing called the explore-exploit trade-off, or the value of information. So there's a classic problem. You're trying to figure out where you should go for dinner. Sadly, this example was made in the before times when going outside was socially acceptable, and you're trying to choose whether you should go to your favorite restaurant or whether you should go somewhere new. And this is a surprisingly hard problem, because if the other place is better, this is awesome, you'd love to go there. If the other place is worse, then you don't want to go there. It's probably worse because you know you really like your favorite place, but it could be better, and this is a trade-off. And I think there are a few important things you might think about when figuring out how you trade off between the two. So one, length of stay. Am I going to be in this town for the next 20 years, where it would be insanely useful to me to find out another restaurant I like more? How certain am I about other places? Like, have I tried other places? Have I tried this place before? Is it completely new? Do I think that like it's just got a new cook, so maybe it'll be a bit better? Or have I been to everywhere else like at least 5 times and I'm just very confident they're crap? Like, you want to spend a lot more effort exploring if you have high uncertainty. And it's only really worth exploring if somewhere else could be better. Like, if I've already visited 1,000 restaurants and this one is the best, it's not that likely that a new restaurant's going to be better. Well, if I've only been to 5, like, I'd love to explore more, because 5 is a really small sample size. And these are like some of the key things to bear in mind when we're thinking about how to get a computer to make this trade-off. Yeah, and like the key thing to bear in mind is that you're always trading off your value now to maximize your future value. And you only want to sacrifice value now if you think it actually might help maximize long-term value. And the way we formally describe this is with these 2 key terms, explore and exploit. Exploring is trying something new. Exploiting is doing the thing that I currently think is best. With reinforcement learning, this is a really important thing to bear in mind, because it's really easy to get stuck in bad local optima, meaning you find a strategy, the strategy is kind of okay, there are much better strategies, but it's like hard to go from your current strategy to a better one. So this is an example of what happens if you don't explore enough. This is apparently a cheetah that was being trained to learn how to run. And it figured out pretty early on that if it flipped over, it would briefly be going fairly fast. And so it just got really used to flipping over. And then from its back, it figured out that it can run like this. And the speed it gets right now is about a third of the speed it would get if it was running the right way up. But when you're stuck like this, it's really hard to figure out that you should like flip over and run like that. Because you're really good at running on your back. You kind of suck at running on your front. And the key challenge is, how can we make programs that are better at this? And on the flip side, sometimes if you make things that are good at exploring, it can learn cool strategies. So this is an Atari game where DeepMind trained a bot that learned, it spent a while just like chipping away at the front blocks like that. And then it eventually learned that if it sends the ball behind the blocks, it now gets like way more points. And it took ages for it to learn this. And the challenge is figuring out how you can make a program that will actually continue to explore, even when it's pretty good, and learn how to do new things like this. This is a really hard problem. So one of my favorite quotes is that during World War II, this was sufficiently hard that the Allies were considering dropping the problem in Germany, so that German scientists could also beat their head against it. And it's really hard because you need to balance, but you don't have the information to know how valuable it would be to explore more, because there is cost to getting that information. So the theoretical framework we use to understand this called many-armed bandit problems. Actually, I think it's called multi-armed bandit problems. That's a typo. So the formal setup of this problem is you have a bunch of, say, slot machines, and the payoff of each slot machine is random, but the distribution is fixed. It doesn't change over time. Like, say, every time I pick a slot machine, it just tosses a fair coin, and if the coin is heads, it gives me 1. If it's tails, it gives me 0. And the other slot machine is a biased coin that has bias of, say, 2/3. And I have no idea what these biases are. And the problem you want to figure out is, how can I make a program that learns the optimal way to pull these levers? I think this is an interesting problem to think about, because it only abstracts out the explore-exploit trade-off. I start out with, like, say, 3 slot machines that I know nothing about, and maybe I try each one a bit. I think the first one is the best. I need to figure out how I can trade off effort of pulling the first lever against time spent pulling the other 2 levers, just in case they're actually better and I got unlucky. And this is a useful framing because there's no long-term planning. Like, I'm just picking the levers I want to pull. In an ideal world, I would just only pull the lever with the highest expected value, but I need to figure out what that lever is. And there is a lot of literature around this problem. I'm going to try to summarize some of the basic ideas of the main solutions, and I highly recommend reading up more on the literature about this if this interests you. I'm going to give a very brief summary, and I'll link to more resources at the end. So, by far the worst solution to this problem is just not exploring, picking the thing that you think is best and just always going with that. This is terrible because let's say my problem is I've got 2 biased coins, I don't know the bias of either, and I just want to figure out which one's best and toss that a million times. I might toss each once, find out one gives heads, the other gives tails, and I decide I should go with the one that gives heads, and I toss that a million times, and I just will never learn that this was a bad idea. A slightly more sensible strategy is what I'll call dumb exploration. And the idea of dumb exploration is at every step, with some probability, I'm going to just pick a random action. And otherwise, I'll just pick the best thing. This is like This is called an epsilon greedy approach, because you just write down a probability epsilon. With probability 1 minus epsilon, you're just greedy and you take the best action. With probability epsilon, you choose something random. And this like sounds kind of dumb, but this actually is like a pretty good algorithm. There's lots of cutting edge reinforcement learning approaches that use like some small variant on this. So one intuition for why this is actually an awesome algorithm is that you're basically just choosing some fraction of your like total lifetime payoff that you're just throwing away because you're going to do random actions, say 1% of the time. And this means that as time goes to infinity, you're almost certainly going to find the best thing to be doing, because after a long time, you'll have tried everything. And you'll have tried everything a fair amount of times, and you'll be pretty confident what's the best. And this is incredibly easy to implement. And so the amount you can lose out just isn't actually that high. But we can do better. I'm going to call the ways you can do better smart exploration. So the way to figure out how you might do better is by thinking back to the start of this chapter, when I talked about the reasons you would want to explore more or explore less. And generally, you want to explore more when you have a long time left, when you don't have a lot of data, and when you think other things could be better. You can implement these in this algorithm. Two interesting tweaks you can make are just decrease epsilon over time. Say epsilon begins at 1, and then at the end, and then you like linearly decrease it to 0, because the less time you have left, the less viable it is to explore, and so the less you want to do it. And that's also really easy, and it's actually a notable improvement. Another thing you can do is called choosing the highest upper confidence band. So in this version, you'd say model the reward of each bandit as a normal distribution, and just you'll have a bunch of past data, you'll calculate the mean and standard deviation, and you'll say, what's the 95th percentile of this distribution? And you pick the distribution that has the highest 95th percentile. And this is actually a surprisingly excellent approach, because if you have very little data, you're going to get like a very, very broad distribution, which means the upper confidence bound is going to be pretty high. Well, if you've sampled something like 1,000,000 times, it's going to look more like this. Like you're really, really confident you understand the distribution. And the 95th percentile thing is like here. So if you have a bunch of distributions that are kind of close, when you haven't done them enough, you'll kind of systematically select the ones where you don't have much data. If it's blindingly obvious that something is the best, then you'll go with that. And if it's not blindingly obvious, then you'll kind of like fairly evenly go between things, because the more data you get, the less likely you are to pick it. And over time, this is just going to converge really, really well. I think this is like a fairly satisfying and poetic solution, because this is basically saying that a pretty good strategy in life is just being an optimist. Doing the things where, like, you know, in a really good world, this would be great. This would be the best thing to do. And over time, if it's a bad idea, you'll get burned and you'll stop doing it. And sometimes it's a good idea and you can just keep doing it. And I find this satisfyingly poetic. And so another reason I think this is interesting to think about is explore exploit is incredibly relevant to how humans live and make decisions, because we are in a sequential decision-making process. We lack a lot of information. We want to maximize the value of our lives, and we don't know how. And we need to think about how to make this trade-off. So, like, this is obviously true in the example I gave at the start of restaurants, but I think this expands way beyond that. So some of the areas where you most want to think about this are areas where you have a lot of time left, which for students are just things where you'll be getting value over the entire rest of your life. I think two really big examples of this are your career and your love life. Information in those two areas is incredibly valuable. I think one really common mistake I see people making at Cambridge in the Cambridge Maths department is just assuming they want to do a PhD because everyone does a PhD and it's the done thing. And I think that this is like a massive failure on the explore-exploit trade-off. Like, you have the rest of your life ahead of you. This is like 40 plus years. Information you get now about how to spend that time better is insanely valuable to you. And I think this is like a really important question that people should think more about. Personally, I'm incredibly uncertain what I want to do with my life, and I'm basically taking the next year to explore and try other things. I think two doable ways to implement this in your life are just notice when there's a really cheap way of getting more information about something and do it. Like something you've never done before, somebody who has some interesting experience you could ask them about and learn more from them, and try to bias yourself towards doing things more. Like doing things that are a bit outside your comfort zone, where you do it once, maybe it's terrible, you never do it again, maybe it's awesome and you can do it loads. Like, I think basically everyone should try out at least 10 hobbies, because if you find a hobby that's awesome, you can stick with it forever. If you don't like it, yeah, it's like you failed once. Like, go to a swing dancing class, go to a salsa class, go to a cooking class, just try things. So another reason I find this really interesting to think about is, so we want to come up with a way of getting a program that will decide to explore on its own. And I think that a really good way of getting this to happen is by giving a program a sense of curiosity and novelty. Like, you just tell it new things are cool. Go and like think about new things and do new things. And I think this is why humans are curious. This is why humans like new things. This is an evolutionary successful strategy because it means you have organisms who are in a sequential decision-making process and who explore and get more information. This is actually an approach that's used in reinforcement learning problems. And this runs into an interesting problem called the noisy TV problem. So the way you try to encode this is you have the agent have a model of the world, and then you tell the agent, hey, here's your model of the world. Notice the things that don't fit this model, and we'll give you a reward when you observe something that you didn't predict, something that surprises you. Naively, this seems like a pretty good way of training it to like do new things and things that are outside of the world it currently understands. Like if you've like spent your entire life in the UK, then going to France would be like massively outside your model, and so you'll be rewarded for like going to new areas. And a hilarious thing is called the noisy TV problem, where so some people trained an agent to explore a maze, and on one wall of the maze they put a noisy TV, so just like random images, and in the world without the noisy TV, the agent did pretty well, as you can see. But in the area where it had a noisy TV, it was like, oh, I can't predict this. This is really exciting. I'm just going to like sit there and become a couch potato and just stare at it. Interpret from this what you will. So to recap the important points in that chapter, RL is about a sequential decision-making process, which means that information is valuable because you can take better future actions and you can break out of bad local optima. This is a difficult trade-off, and the main way to resolve it is by exploring some of the time, because you don't really know whether exploration is useful or not. So you need some balance. You want to explore more if you've got a long time ahead, and if you have a high uncertainty, or you don't have much data. And this is really relevant to just thinking about life, because most people systematically fail to explore enough. Cool. So now I want to think about a different problem with the reinforcement learning, which is the problem of how you specify the reward. like how you set up the problem so the optimal strategy for this reward is the thing that you care about. This is really important because programs are awesome at optimizing the reward that you give them. But if you don't give them the perfectly correct reward, this is just terrible and it goes wrong. And so you really need to make sure the reward is tied to the thing you actually care about. And this is hard because you need to give a reward that's clear, numerical, easy to calculate. And this can often bias you towards simple, easy rules, and this can lead to problems, as we'll see. This is one of the reasons that some of the initial exciting progress in reinforcement learning came from Atari. So these like simple video games, because the goal in Atari is just maximize your score. And this is an incredibly easy reward to specify. And this can go wrong. So, and this is a problem called specification gaming. This is an extremely famous GIF where some people at OpenAI were training a boat to play this racing game. And the boat got scored depending on like how well it did, power-ups it hit, etc. And it turns out that a more efficient way of maximizing your score, rather than trying to win the race, is just finding some power-ups and going in an infinite loop at exactly the rate the power-ups will generate, and just never finishing the race. And it's, I think this is like, this is a hilarious problem. And it's easy to see this and just be like, oh, those designers were dumb. They didn't design the right reward function. They should just try harder next time. But this is a really, really common problem. So another type, here's a robot. The robot was trained how to walk, and it learned that if it hooked its legs together, it could move pretty fast in a really easy, low-effort way because there was a bug in its physics simulation. And there's a list of at least 60 more examples that I'll link to in my resources. Like, this is a really big problem in the contemporary field of reinforcement learning. And this gets kind of concerning sometimes. So there was a lot of drama around things like Facebook and YouTube recommender systems, where, as far as I'm aware, these were trained with reinforcement learning to maximize the probability that a user clicked on the videos. And the problem the designers actually wanted to solve was show people things they'll like watching. But it turns out that a way more efficient solution to this is make people into the kind of people who really, really like watching things. And it turns out that a surprisingly efficient solution to this is get people who are really into conspiracy theories and just like things like that, and will just want to watch endless videos. And this is just actually a pretty concerning social problem. And this is what happens if you don't specify your reward correctly. I also think that, so it's easy to look at problems like this and just say, oh, these are machines, the machines are dumb, they're just blindly maximizing the rewards, they don't have common sense. If they had common sense, they would just know how to do things well. But I think that's a pretty limited way of looking at the problem. And I think this actually teaches us a lot about how we make decisions. So there's an idea called Goodhart's law. This is outside of reinforcement learning. This is just like a truism from economics and social science, which says when a measure becomes a target, it ceases to become a measure. What this is basically saying is that people respond to incentives. If you try to come up with some kind of proxy for what you actually care about, and people are aware that this proxy exists, they will try to maximize for that proxy, not what you actually care about. And if people are optimizing really, really hard, they'll often go really far away from the original thing you cared about. Because maybe your proxy correlated with the measure you cared about when nobody was trying to optimize for it. But when you're trying really hard, you just completely lose track of the original thing. Some examples of this. There was a case in colonial India where there was a cobra problem. And the government said, we'll give a bounty for all cobra corpses. And shockingly, what happened is they got loads of cobra corpses, and this was awesome, until they discovered the cobra farms. There were instances with Soviet factories where they had quotas they had to fill out for things like the number of nails they produced. But nobody specified the size of the nails, and they had limited resources, and so they made the smallest nails they could possibly produce. I think this comes up in exams. Like, you have A-levels. A-levels are these like big exams, and they determine the university you get into, and scores are scored depending on how people do in these exams. And the exams are supposed to correlate with learning, but why would you teach people actual, like, interesting content if you could spend more time teaching to the test and ensuring that they learn better? Like, I think this also comes up a lot at Cambridge. We have this incentive structure of exams. We're here to learn maths, and it kind of correlates with how well you do in exams. But if you're trying to optimize your exam performance, these diverge a lot. And I think this just actually comes up a lot in personal life. So some things I observe in friends, you get people who, their goal is to learn maths. They have a proxy goal of going to lectures. They maybe miss a lecture because they're ill, or they're just a bit behind, and they're confused, but they keep going to lectures because lectures are how you learn things. You get people who go to university and say, I'm here to make friends, and I'm here to meet people. How do I meet people? Like, how do I get quality social time? I meet lots of people. How do I meet lots of people? I go clubbing. They don't actually enjoy this, but this is the proxy for the thing that they care about. And you've got to optimize for the proxy, right? Maybe another one is people who decide, I want to learn cool things and be intellectually engaged. And so they go to random talks in their spare time, like listening to some guy chat about reinforcement learning and ramble for ages, when what they actually care about is learning interesting things. If you want to leave now, I will take no offense. Like, I see this in my life. Like, I'm a pretty big completionist. I tend to take a proxy goal of finishing the things that I'm doing. I'll start a course. I'll discover the course is actually kind of crap and I'm not learning anything. But my proxy for learning cool things is finishing courses, so I want to drop it. Or I'm reading a book and the book isn't actually that interesting, but I confused learn worthwhile things and be intellectually engaged for the proxy of read lots of books. And I think the main way to solve this is just think about what you actually care about and ask yourself, am I optimizing for a proxy, or is this actually linked to the thing that I care about? And if you feel a bit frustrated or things feel like they're going wrong, maybe you're Goodharting yourself. So with that pontification aside, what can we do about this in the world of reinforcement learning? So, as I said, I think this is a pretty big social problem. Stuart Russell, a professor of AI who literally wrote the book on artificial intelligence, calls this the standard model of artificial intelligence. Like simple reward functions that we write down and tell machines to optimize. And there's like an active and really, in my opinion, really important area of research that's thinking about what we can do about this to come up with the reward functions that will actually generalize to the real world. One approach I think is interesting is called value learning, or learning human values. So you might train a program to like observe people and learn to imitate their actions. And here your reward function is basically how close are you to the way humans do things. Another thing you might do is tell it, you're really uncertain about your reward functions. You should have a distribution over reward because you're probably going to screw things up. And you should just like keep checking with humans whether you're doing the right thing or not. Another approach I think is interesting is trying to redefine the idea of what a reward is. So like, rather than simple rules, you tell it, go to a human and ask the human, am I doing good or not? And like, that can just be your reward. You have an agent and you tell it, maximize probability human says yes. Here is a noodle that some people at OpenAI trained to backflip by having it show people a video of itself and say which of these is closer to a real backflip. And I think this is a really interesting piece of research because asking humans to evaluate things is really expensive and really data inefficient, and these are both terrible. And they managed to train the program to only ask when it was maximally uncertain. And it only asked the human 900 times. And by just like finding the videos that were like most confusing to it. And I think this is a pretty good backflip. Like, seems legit. So, to recap the important points in there, the solution to the problem is fundamentally driven by the reward. Specifying a good reward is hard, especially for real-life problems. This is pretty relevant to normal life because of Goodhart's law, where you set yourself a proxy, which isn't what you actually care about. And this is a really interesting and active area of research, of finding ways to define rewards that actually capture what we care about, rather than this standard model of really simple, messy thing, of like really simple, like things that miss the things we actually care about. So that's the end of part 1. People have any questions?
Neel, could you talk about like what sort of flavor of maths comes associated with these problems?
So I'm going to try to talk about that a bit in the second half. So I'd say it's pretty similar to function approximation. So a lot of the techniques are about that. There are techniques about things like solving combinatorics problems. So like solving recurrence relations, thinking about sequences. Often you're thinking about games, like say chess. You want to think about it as a tree. Like you start with the blank chessboard, and then you move pieces, and each move kind of represents like a different next branch of the tree, and you have like an enormous branching process, and you want to figure out how to like efficiently search or approximate the tree. Generally, I think ideas from probability come up a lot. Probability optimization. Sorry, the first half was maybe a bit too philosophical, so I'll try to actually have some maths in the second half. Cool. So how do we actually do anything? So first, I want to think about different types of reward. So first, just a reminder of the difference between reward and value. Reward is a number you get after each time step, and value is your total reward over all time steps. You care about maximizing value, but in the moment, you only know the reward. So the immediate reward is useful because it can give you information about future rewards, and often you're pretty uncertain about long-term plans, and it might make sense to just do the best thing in the moment. But generally, the thing that always maximizes the reward in the moment isn't the optimal approach. So our goal is to learn an agent or a function, which is basically takes as input the state of the world and outputs a policy. So a policy is just a way of taking actions and we would like this policy to maximize value. Often we represent a policy as a distribution over possible actions. And there are 2 interesting types of reward. The first is called a shaped reward. So this is where each time step you get useful information. Often the score in a video game is a good example of a shaped reward. Or you have a coach who's directly telling you, say, oh, that action worked well, like that chess move was great, that chess move was terrible. And in contrast to this is a sparse reward. So this is where the reward is only received at the end. So say you're playing a game of Go or chess. You might make lots of moves in the opening, in like the kind of early game of chess, and then at the end, you either win or you lose. And you may maybe like 100 moves over the course of the game, and you don't really know which move best achieved your goals, or which move didn't. Like, maybe you screwed up the early game, but then did really well in the mid game. Maybe you crushed it in the early game and your mid game was kind of weak. All you know is you won. It's difficult to assign credit. And so as a very general rule, it's much easier to learn from shaped rewards. So one reason for this is this idea I've alluded to earlier of local optima. If you're doing something wrong and you only get a reward after doing the right thing for like 100 time steps, it can be really hard to explore hard enough to learn about this other route. While if the moment you start taking like first steps along that journey, you get feedback saying this is awesome, keep going, it's much easier to do that. On the flip side, often a sparse reward can better capture the thing you actually care about. Like this is the root behind a lot of the reward hacking or specification gaming we saw earlier. And I think the same kind of trade-off applies for humans. The equivalent of shaped reward is a tight feedback loop, something you do where you just get really regular feedback, and you see how well you did like very frequently. And I think it's worth bearing in mind that if you want to learn how to become good at something and you're finding it hard, often one of the determinants of whether this is like good, one of the things that can help you learn efficiently is getting feedback like well, fast, and that's very closely tied to the actions you took. This is called the credit attribution problem. This problem of you get a sparse reward at the end, you don't know what actions you took from it. This is a big problem in things like marketing, where, say, you show a lot of ads to you show lots of different kinds of ads to people, then people eventually buy your product, and you don't really know the thing that you did that worked well or didn't work well. You just kind of have to guess and pray. I think this kind of thing is also where a lot of superstitions come from. Like, you step over a black cat, and then you get fired from your job. And you don't really know the things that you did that did or did not lead to this. And it's really easy to, if you have like a badly programmed reinforcement learning agent in your mind, like humans do, to misattribute the various things that led to the eventual problem as being causally linked to it. So what can we do about this? So now I'm going to dig a bit into how you actually train things. So there's a method I hope people are familiar with called gradient descent, which is just you've got a function you want to fit to some data, or you've got like a function you want to minimize, and you take the input to the function, you differentiate with respect to that, you find the gradient, and you just like slightly adjust that parameter in the direction of the gradient. And what you're basically doing is taking a curve or a big many-dimensional surface and looking in the downwards direction and just like stepping a bit in that direction. And this is a really effective method. And this is the core behind most of modern machine learning. This is significantly more effective than it seems when you first come across the idea. And we can basically use this method to train a reinforcement learning algorithm where we've got a function that maps state of the world to a policy, and we find the reward for that policy, and if it's a shaped reward, then we want to update the policy with the gradient, but we can multiply the gradient by the reward. And this works surprisingly well because it means that if you do something really, really awesome, you update a lot that that's a good idea because you've got a really high reward. If you do something like a bit awesome, you update a little bit towards being a good idea. And if you do something bad, you update in the opposite direction. There's a bunch of mathematical theory behind why this is this is like actually an awesome idea. This is called the policy gradient theorem, and I'll link to some resources at the end that tell you more about this. There's an excellent reinforcement learning textbook by some people called Sutton and Bartow that explores this. But for now, the intuition of just you want to step in the direction that like gets you things that you want. If you're getting positive reward, you want to step really far in that direction. If you're getting negative reward, you want to step away from it. And this basically works. And this works really well if you have a shaped reward. Because after each action, this tells your network, oh, that action was awesome. You should take that action again. Because it's got like a useful reward tied to it. Now we want to think about how we can extend this idea to a sparse reward. Like, I want to be able to play a game of chess, and at the end of the game of chess, be told you win or you lose, and update towards doing the things that made me win. And this is hard because I'll have seen maybe 100 different states over the course of the game, output 100 different actions. And there is a beautiful, glorious hack we use to solve this problem, which is to pretend that the game we played was a shaped reward game. Have these 100 instances of state of the game action pairs, and then at the end of the game, go back, pretend that at each one of those, we had the shaped reward of did I win this game at the end? And then apply the algorithm from the previous slide. So if you win the game, tell your network, every move I took in this game, that was great, make that move a bit more in future. If you lost, tell the network, every move I took in this game, meh, that was bad, I shouldn't take that in future. And you want to train this in batches. Meaning, like, you get the 100 moves over the course of the game. You don't know whether they were good or bad until the end of the game, but then when you know, you can go back and update on all of them. And this is a massive hack. I think it's reasonable to be skeptical that it works. One intuition for why it should work is that, so some moves you take are basically neutral. Like, it's not amazing, it's not terrible. Some moves you take are terrible, and some moves you take are awesome. And on average, you are more likely to take the awesome moves in games that you win, and more likely to take the terrible moves in the games that you lose. Kind of by definition. And so if you play enough games, you don't update too hard on any individual game, but you update loads over time. You'll kind of, on average, learn how to take actions that work. And there's a lot more mathematical theory that you could do into this, but I couldn't think of a way that to present a talk that was at all interesting, because presenting maths via PowerPoint is hard. This works. So this is a YouTube video of a Pong playing bot that somebody trained with this technique, and I'd say it's pretty good at Pong. Though it's also very weird and very jittery. And there is an excellent blog post I'll link to in the resources section, which explains like how this works and why, and digs more into the intuitions behind policy gradients. Some limitations of this, as I said, it's incredibly sample inefficient. Another reason is that you need data to learn something as good or as bad. This leads to what we call the safe exploration problem, where there can be things that are just really bad, and you don't want this to ever happen, where the agent can't learn it's bad until it does it, like crashing a car or killing people. Or take a more mundane example, you're training a robot to clean a house. It needs to learn that priceless vases should not be pushed over to access the dust beneath them. And you really want it to learn this without actually having to do that. More generally, this is like a really blunt brute force technique that doesn't really use any knowledge of the problems you're facing. Like, we trained it, you can train an agent to play Pong doing this, and it knows nothing about, like, it's got a bat, the other opponent's got a bat, the opponent's playing the same game as it, there's a ball that wants to get to the end. It's just seeing arbitrary pixels coming in. It knows nothing about, like, physics, it has no human intuitions that a human would, and it's just learning how to do this well. I think this is both a limitation and kind of really impressive that it can learn how to do this. Yeah, it's also pretty easy to get stuck in local optima when doing this. So to recap the important ideas in that chapter, there are two types of reward: shaped, where you get useful feedback at every step, and sparse, where you only get feedback at the end. It's generally easier to learn from shaped reward and hard to get stuck in local optima. There's a technique called policy gradients, where you just pretend a sparse reward is shaped and train in batches, and it's really noisy, but it basically works, and it's amazing and also terrible. So now I want to talk about something called Q-learning. Just a note, we've been talking a lot about games so far. I think that like a lot of the examples we'll see of reinforcement learning are games. A few reasons. They're easy to simulate. People like games and find them fun, so it's more impressive to do things with games. Like, solving Go was an incredibly big deal. It would have been less of a big deal if Go wasn't a massive cultural thing. Often in games you have perfect information and a really clear reward and utility function. I think it's pretty reasonable to be skeptical when saying things like this. But I think there's been some pretty interesting progress towards more complex low information games, like StarCraft and Dota, where you have limited information, it's really expensive to simulate, their reward is like it's a really long game, you need to care a lot about things like long-term planning, and somehow people have trained agents that are actually good at this. But yeah, I think it is reasonable to be somewhat skeptical of playing games as the main thing people are doing here. And so now I'm going to go on a bit of a tangent, talk about an idea called dynamic programming. This isn't really an idea from reinforcement learning, this is just like a general idea for computer science. So here's a problem. We've got a robber. The robber wants to rob houses. It wants to maximize its total money, but it can't rob two houses that are adjacent. And it wants to figure out the optimal way of doing this. When you look at this problem, it's pretty obvious that you pick the $10 and the $2 house, and that maximizes your value. A naive way you might think about doing this is recursion. So for the first house, you say, do I do this or do I not? The world branches. For each branch, you then say, do I do this or do I not? So you go from 2 states to 4 states. Next time you have 8 states, etc. And for a 5-house problem like this, that would actually work pretty well. I think there are also some pretty obvious problems with this, because things branch and things get very big when they branch. But if you look at this problem, if I rob the first house, I know that I can't rob the second house, and I need to figure out the best way of robbing the last 3 houses. If I don't rob the first house, and I don't rob the second house, I still need to figure out the best way of robbing the last 3 houses. These are the same problem. And so rather than having a massive growing exponential tree, I can just save my work when I got there the first time and use it in these other places. This core insight of just find a way to describe all of the relevant information and save it is called dynamic programming. And if this seems like too simple an idea to be spending this much time on it, yeah, you get the idea. It's just pretty simple, but makes a really, really big difference. And the key insight behind this is that if you want to find the optimal solution to a problem, a lot of the time, any kind of sub-solution to that must also be optimal. So the best way of robbing 5 houses, if you want to rob 5 houses and you want to rob these 3 houses, the best way to rob all 5 houses as a sub-problem, also find the best way of robbing these 3 houses. And the general insight to get from this, for the purposes of reinforcement learning in games, is that if you want to learn how to play a game optimally, it's a places to know how to play the game optimally from any state, because you can then look at all possible next states and just choose the next state where, given optimal play, you'll do the best. This actually kind of works in some cases. You can solve noughts and crosses with an approach like this. And the rough picture to have in your head is that you just make a table of all possible states of the world. You look at all possible end states. You write down the value of the end state, and then you go backwards and try to fill into the table from once you understand all of the terminal states of the game, you look at things one step back from the end state, and you say, what are possible next things I could do? I find the best one of those, and this lets me just fill in the best value at things second from last, and you can just keep stepping backwards. And this is like worth understanding, but also obviously pretty limited, because you're going through every single possible state of the game. And if you imagine a game like, say, chess, this is just obviously impractical. And another reason this is impractical is you kind of need to perfectly understand the environment you're in and the game you're playing to solve this. And so we want to kind of try to rescue this key idea of optimal, any subpart of optimal play is optimal, while addressing these problems. So we'd like to extend this in two ways. One, we'd like to be able to do dynamic programming, but going forwards in time rather than backwards in time. Like, I don't understand what the end states of the world are, such that I could work backwards. I'm just in an environment, I can do things, and I get told how well they did. And that's how I get information. And I would like to be able to learn by doing things and seeing what happens. And I can't really do an exhaustive search where I just get perfect information about optimal play. So I'm going to need to be more efficient, and I'm going to need to approximate. And the key idea behind how this works is a technique called Q-learning. So in Q-learning, we introduced this new idea called a quality function. And the quality function is basically going to tell me, at any point, given any state of the world, and any next action I'm considering taking, what do I think the total value will be if I take that action from that state? And this is basically the same thing you would get from dynamic programming. If you know from a state, for all possible actions, what the expected reward would be for each action, you can just take optimal actions. But obviously we can't just perfectly calculate this, because we want to do better than dynamic programming. And so we need to approximate it. And the idea in Q-learning is that you have an approximate function. It starts out with some really dumb initial value, and over time you want it to slowly converge to a good, useful value. And we want to try to borrow some of the ideas from dynamic programming to do this well. Note that because we're looking at things like pairs of states and actions you could take from that state, this is what's called a model-free reinforcement learning algorithm. You don't have to understand what's going to happen after you take an action. I don't have to know the rules of chess and say that when I move my pawn 2 steps forward, then I'll get a chessboard where the pawn is 2 steps forward. I can just output the action, and the environment will tell me what happened. That was a terrible example. I'm going to give a better example. If I'm playing a game where I'm trying to, Space Invaders, and I'm trying to shoot the fast-moving ships, I don't have to have a perfect model that I'm shooting a particle. The particle's going to take a second to get to the top, and the thing's going to have moved 50 pixels in that time. I just know when I press shoot at this time, most of the time it hits an enemy. Or I get points. So our goal is going to be to find a good quality function. Looking at the time, I am definitely going to overrun. My apologies. So how do you actually do this? This part of the talk is going to get a bit technical. This is the most technical section, so don't worry too much if you don't really follow this, but I'm going to try to give the broad strokes. We start off by initializing our quality function. We come up with rough guesses for the expected value from certain state, from every state action pair. We then get a bunch of data. We play the game. The exact way we play it doesn't matter that much. You might just always choose the action you think has the highest expected reward. You might just choose random things. There's a bit of an explore-exploit trade-off here. But every time you play a game, you get a bit more information about what the expected reward is after each action. And we then update our estimated quality with the new information we get about how we played. And you just keep doing this. And if you get this right and do this enough times, you can end with a pretty good understanding of how things work. This complicated equation is the actual approach that gets used to update the information. The important parts of this is that we kind of fudge our old quality. So this equation says, if I'm in state st and I take action at, so I'm at time t, then update the estimated quality by taking the reward that I get at that time times the best reward the kind of q function, the q value I could get at the next state given optimal play. So like the maximum possible like future value I could get after taking this action. And so this is my guess for this is my new guess for how valuable things would be. And I multiply it by a pretty small number because this is going to be noisy and I don't have very high confidence. And I just slightly update. And this is an interesting equation because this function q is an approximation, but we know that there is going to be some true function out there that is if you have the optimal strategy and you will take the optimal strategy at all future time steps, what is your expected reward from this state and given this action? And that optimal policy will be is going to be the limit if this process converts to something over time. The optimal function will satisfy this equation. If you take the optimal action and you get some reward and your future values are accurate and you look at the best one of those, then this equation just won't change if you have the optimal function. It will change if you don't have an optimal function. And so this is a pretty theoretically principled thing you might be doing, because you have an equation you're updating. If it's going to convert to something, then there's a good argument to be made that it can only converge to the optimal thing. There's a lot of theory I'm skipping over here. This is pretty related to ideas surrounding stationary distributions and Markov chains, and I will link to more resources so you can read about this kind of stuff. So this is an interesting approach. A lot of the modern, actually effective approaches to reinforcement learning rely on this core idea. The Atari games I mentioned a few times, and the brick-breaking game I showed at the start were trained with variants of this approach. It also has a bunch of limitations. So initializing your Q values is hard. This is a recurrence relation. You're initializing your state at something. You're then applying a recurrence relation to it. And we know from, say, differential equations that the initial state, things are really sensitive to the initial state. And we also know that it's kind of limited because it only really works if things converge to something sensible over time. And it's easy to get into unstable trading dynamics because if you look at the equation, there's a decent chance you can get a kind of garbage in, garbage out problem, where if your Q values are complete garbage, you're exploring in the wrong directions and you're getting the wrong information. Say you think there's actually a best action, but you think it's a crap action and you just never take it, that you'll just never get the right information about how good the current state is. But there's a lot of interesting work that's gone into trying to find ways around this. So another limitation that I've got to put on the slide is the function as I've described it so far is just like a massive data table. for every state and action, we're tracking a value, and we update that value every time step. Every time we're at that state and take that action. And there's a phenomenon called the combinatorial explosion that happens where if you're trying to think about all possible states in a game, and it's a sufficiently complicated game, things go incredibly fast. Like in chess, on average, you have about 30-ish moves you can take. 30 is fine. If you have 10 moves in a row, there is 30 to the 10 possibilities you can get. Picture to have in your head is just like a massive branching tree, where rather than having a termination at each thing, you have like even more tree. And this basically means that any tactics that have a data table are just like completely impractical. And this is called the combinatorial explosion, which is a delightful name that makes me happy. And so one solution to this is this idea of function approximation. So we really don't want to store a massive data table. What we'd like to do is have some much simpler function that we can parameterize with many fewer variables that can try to approximate a data table. Like you give the function a state action pair, and it outputs what it thinks the quality of that state action pair is. And if we can make it simpler, then if we think there's some, like, say, hidden structure of the game where different states are just pretty similar, then we can have a much simpler function that can learn from lots of different states what the underlying structure of this quality function is. And we've now turned this from a sequential decision-making problem to a kind of machine learning problem. You have inputs, you have outputs, you can estimate the outputs, and you want to try to fit a simple function to approximate these inputs and outputs well. And conveniently, this is a problem that neural networks are excellent at. And there's a fairly new technique developed in the last few years called deep Q learning, where your quality function is a neural network. And we replace this standard update step that I mentioned earlier with giving your neural network a new training instance, where you tell it, oh, for this state action pair, here is a new guess for what the expected reward could be, and it slightly updates to predict that a bit better. And if you have a nice, well-structured game where there is something to be understood about mapping states to actions, state and actions to reward, then you can get a lot of value out of this. And this is the technique that DeepMind used to like do really well on Atari games. To recap the important points in there, if we know the optimal play from all possible next states, then we can play optimally. This is the key idea of dynamic programming. You don't need to know like what the entire rest of the game would look like. It suffices to just look one step ahead. If you already know what's optimal from that one step ahead, this does not generalize because of the combinatorial explosion. Q learning is a technique that tries to approximate this with a kind of incremental update method that uses the ideas of dynamic programming, but starts with an approximation and hopes the approximation converts to something good over time. And if you add in function approximation, then you can get a lot of the value of these basic ideas, but you can get a lot of value of these basic ideas in a way that's actually practical and actually works. Okay, so I'm now 2 minutes over time. So I think what I'm going to try to do is skip to the conclusion, give like closing thoughts and room for questions, and then give some of my remaining content as an encore. Feel free to remain around for that or not. Is that okay with the Archimedeans, Yuri?
Yeah?
Cool.
Yeah, that's fine.
Okay, to conclude, the key ideas of reinforcement learning are that it is a class-old optimization problem. You, rather than instructing the program about what to do, you give it information, and about what worked and what doesn't, and it learns how to try things and to do things, and from this feedback the good actions get reinforced and the bad actions get negatively reinforced, and over time it learns to be competent. There are lots of really interesting challenges from this because it's a sequential decision-making problem, and there are many different types of solution and ways to attack it. And this is a difficult problem. It's a work in progress, but it seems to be like a really interesting and promising field, and it's growing a lot right now. Some of the key considerations to think about when understanding the problem of decision-making and what you can learn from them. Information is really valuable. Information has a cost. You can try new things and learn from them, or you can do the thing that's currently the best. This is a trade-off we all face every day in our lives, and need to learn how not to get stuck in local optima. Getting the right reward function is really hard and can really mess up your program. And it's important to remember the things you personally actually care about and whether you're confusing those for proxies. There are different kinds of reward, and you need to if you have a sparse reward, you need to be able to understand long-term planning and be able to kind of do things you don't really get feedback telling you whether what you're doing works or not. And this leads to a lot of problems, like the credit attribution problem. You just don't know what to learn from your experience. And one way that you can try making life easier for yourself is looking for things with type feedback loops. And so I've tried to make the case in this presentation that reinforcement learning is really interesting. There's loads of cool shit in there to understand, and hopefully this has resonated with some of you. In which case I'm asking, like, what could you do to learn more about this? So one of the reasons I think this is a really, really interesting field is that progress is going off super, super fast. Like, in 2014, DeepMind learned how to solve Atari games. In 2016, they solved Computer Go, which is, like, a really big deal. In 2017, people learned how to solve Computer Go without using any existing human knowledge. More recently, people have learned how to play imperfect information games like Dota and StarCraft. People are trying as hard as they can to do things that aren't games, and hopefully one day I'll have a list of examples that aren't games. And I think that, like, AI is something that's fast growing. There's a decent chance that AI is incredibly transformative over, like, the coming decades. And it seems like as AI systems get more powerful and more transformative, they are pretty likely to be doing things that involve sequential decision-making processes. And this means that there are lots of important problems that are going to come up, and things that are just relevant to society and the future of humanity that really rely on reinforcement learning, which personally I find pretty motivating. You might also just find it intellectually interesting. Some specific sources I'd recommend. I'm going to link to all of this at the end. There's an excellent textbook by Sutton and Bartow that's all about classical reinforcement learning, very mathsy. I think it would appeal to most people in this audience. OpenAI have an incredibly good tutorial called Spinning Up and Deep Reinforcement Learning. This is more focused on, like, modern reinforcement learning, things that use deep learning, and I think it's both, like, really well done, really well explained, and has a lot of, like, code, examples you can play around with, and really get your hands dirty. And I think that's important for understanding things that are more to do with like more empirical fields, and things that are more to do with making programs that actually work. There's an excellent course by David Silver, who's the creator of AlphaGo and AlphaZero. And yeah, I link to all of these and more on my website at neelnanda.io/rl-talk. And I also have a feedback form on there, and I would be extremely appreciative if people could fill that out, because giving talks is a sparse reward problem, and making it as shaped as possible would be highly appreciated. Yeah. Are there any questions?
There was a question in the chat.
Mm-hmm.
Wait, let me just put it again. Yes, it was a kilo learning is compatible with multi-agents?
Huh. So to give context on why that's an interesting question, so multi-agent reinforcement learning is where rather than being in a kind of player versus environment setting, like you're playing an Atari game, you're in a player versus player setting. Like you're playing Go, or you're trading on the stock market, or you're like a car driving amongst other cars. Car driving amongst other cars isn't a great example. There's like something adversarial or like something collaborative. There are other agents who are also learning, and you need to interact with them. And this is much, much harder than like more standard forms of reinforcement learning that I've talked about, because if you'll say, like, by random chance, you end up being a bit smarter than your opponent, you might just learn how to exploit your opponent. I never really learned how to be good at the game, but just like be really, really good at hitting all of their blind spots and just grow faster than them. And so there's a constant challenge of getting the training dynamics right if you're doing multi-agent problems. And some of the hacks people use don't work as well. For example, if you want to play Go, you can often address the multi-agent thing by assuming your opponent is just identical to you, because the strategy for black and white in Go is pretty similar, as far as I can tell. That doesn't work if, say, you're playing hide and seek, and your opponent is a seeker and you're a hider. These are just completely different things. And maybe it's much easier to learn how to be a good hider than a good seeker. So I think the question is less interesting, because in Q learning, we were trying to estimate the value of a state. But the value of a state depends on what you're doing and on what your opponent does. And if you don't understand your opponent, or your opponent is changing over time, then the value of a state is going to depend a lot on like how good your opponent is and how much you know about how good your opponent is. Sadly, while I can explain the question, I'm not sure I can answer the question particularly well. One of the things I'm going to talk about in my encore is how DeepMind actually solved Go with AlphaZero, and that used a kind of variant of Q-learning. Well, it used a variant in the sense of it had a value function that tried to estimate the value of a state, and here it derives a value from how valuable is this if I'm playing against something that's as good as I am. This is very different from the question, how good is it if I'm playing against something that's optimal? Because if it's optimal, it's probably just going to crush me. Sorry, the answer to your question is yes, I think so, though it's harder and there are way more subtleties that go into it. Sorry, that's not a particularly satisfying answer. Were there any other questions?
Yes, there's a question from Callum just now. It says, is there a danger of reinforcement learning changing human preferences in the process of reward maximization?
Yes. So that was basically what went wrong with YouTube and Facebook recommender systems. Like, they were trained to maximize the reward of click rate, and it turns out that a really efficient way of maximizing click rate is changing human preferences to want to click on things more. And this was not the plan. There are some thoughts on what you can do to get around this. Like, for example, you might train a model where you just show a user a bunch of videos, you track whether they click on it or not. You train a supervised learning model to predict the probability the user would like that. And then you train a reinforcement learning model against that supervised learning model. So it can't change the human's preferences because the supervised model is like fixed. But yeah, if you just like do naive reinforcement learning, that can totally lead to things trying to change human preferences. And it's kind of concerning how changeable they are. Any other questions?
Yeah, one more. Just from Cameron. So are evolutionary algorithms useful, particularly for exploring more, or are they inefficient compared to other methods? So evolutionary algorithms.
Okay, so evolutionary algorithms are they're a type of algorithm I haven't talked about. The idea in an evolutionary algorithm is you're not trying to make an algorithm that learns. You're trying to make like a fixed algorithm that just does things on instinct. Like it's got some simple rules in it. But you make lots and lots of these algorithms, and then you run them all on the problem, and you see the ones that are best, and you take those, and you like give them children. Like you create a bunch of random tweaks from things that worked well. You then send them back into the environment. They go off and learn, and you find the ones that are best out of that, and you just repeat. And I think it's pretty obvious why this is called an evolutionary algorithm. And so the main problem with evolutionary algorithms that I'm aware of is that they're really sample inefficient. Like you need to make agents, you need to have lots of them play games, a few of them will work better, and you'll like tweak them randomly. And generally my intuition is that evolution is a pretty crap optimizer, because evolution doesn't know the right direction to tweak things in. Evolution just like changes things, and in random directions you try all of them and you see which is best. One of the reasons gradient descent is so ridiculously powerful and so popular is that it's kind of like evolution in that it makes small tweaks, but it makes them in the right direction. Another problem with evolutionary algorithms is that unless you're training your agents lots and lots of times, things are pretty noisy. Like if you play one game, maybe the dumb algorithm actually does a bit better than the smart algorithm. And this means that you're kind of taking random steps that are on average in the right direction, but you're kind of like going on a drunk random walk that's kind of on average the right way. The main thing I want to talk about now is how the actual algorithm that DeepMind used to solve Go, because I think this is probably the most impressive accomplishment of deep reinforcement learning thus far, and the algorithm itself isn't actually that hard. Except rather than talking about AlphaGo, I'm going to talk about AlphaZero. So the context for this is that in 2016, DeepMind solved Go, where solved means they became better than the world champion of Go. And the way that they solved this was they took an algorithm, they gave it prior based on a lot of human knowledge about how to play Go well, and then with this prior, it then went off and played a bunch of games and became better. But it was kind of building on existing human knowledge. And with AlphaZero, what they did was say, wait a minute, reinforcement learning is awesome. We don't need human knowledge. Can we redesign this algorithm so that it can generate how to play this from scratch? We won't tell it anything about Go beyond the rules, and we'll see if it can learn how to play it. And spoiler, the answer is yes, you can learn how to play Go from scratch better than humans can in like, I think the equivalent of like a few months worth of training. And I think this is both incredibly impressive and kind of terrifying. And so the key question here is, how can you make knowledge from nothing? Like, how can you make an algorithm that can learn and generate knowledge itself? At its heart, this algorithm has a few really basic ideas that were just executed exceptionally well. I'm going to simplify and just give like a very rough outline of the coolest ideas. And I'll link to some more resources if you want to like dig more into this yourself. But yeah, and the other really interesting part about AlphaZero is that it was a really general algorithm. Like the same algorithm worked for becoming awesome at chess and shogi and Othello, and they basically came up with an algorithm that just works for solving adversarial perfect information two-player games and generating this knowledge from scratch. And this is just like really, really impressive. And I'm going to keep saying that because it's awesome. So there are two key ideas in how this works. One is an idea that I'm going to call bootstrapping. So bootstrapping takes a kind of weak agent that's fast and makes a stronger agent from that weak agent that's slower. So this agent, so an agent here is a function that maps, say, the Go board to a policy, a distribution of the future actions. And the question is, how can we bootstrap a weak agent into a better one? The weak agent here is going to be a neural network, which just takes in the board and outputs a distribution of actions. Neural networks are pretty cheap to run, and we can run them lots of times. And to get the stronger agent, what we're going to do is take the current board and just simulate the weak agent playing against itself a lot of times. Then from the simulated data, we're going to then say, okay, so out of all of the games the simulated weak agent played, where it's, say, took move 1, how many did it win? For all the games it took where it took move 2, how many did it win? And just take the move that seems to have the best next action. And so this is clever because so one of the hard problems in a kind of sparse information game like Go is you have to play till the end to see whether something's any good or not. This is one of the reasons Go is much harder to solve than chess. And in order to solve it, you kind of need to understand your opponent. And what this says is just, let's just assume my opponent is as good as the weak agent and just see what happens. And this isn't going to be the strong agent isn't going to be amazing, but it is going to be better than the weak agent. Because basically it has all the information the weak agent has and more. And the kind of key insight here isn't actually all that surprising. Like, it's basically saying, if you spend computing power, you can become smarter. Like, if you run your information gathering process for longer, you can make better and better decisions. Note that when I say simulate it playing against itself, this is done like tens of thousands of times per move. So like, this is pretty expensive, but this is a way to just like spend compute, which we have a lot of, to like become a bit smarter. Sadly, this doesn't generalize because we can't just like spend enough compute that you become awesome at Go. Because that would take more compute than exists in the universe. This idea of kind of playing, of just kind of like playing out random games and trying to infer from this which move is best is called Monte Carlo tree search, which is a term you'll come across if you start Googling about reinforcement learning. The idea is basically you have a tree of like all possible Go board states. You want to explore it and understand the value of each state in here. And you can do this by just like playing random games against yourself and seeing what happens. This is much, much cheaper than actually exploring the entire tree. But if you're like picking random paths through it well, this is going to get a fairly representative sample and thus show you like, I actually kind of have an idea of what the best next move is. That was a terrible explanation. I apologize for it. Don't worry about that point too much. So the second key idea after bootstrapping is training. So we have this weak agent, this neural network, and we want to make it into a slightly less crap agent. And the way you make a neural network better is you give it data. And we want to give it data that kind of plays better than the current state of the neural network. But conveniently, we just figured out how to convert a neural network into a better version of itself. We just like play it against itself lots of times and do this on your bootstrapping. So what we do is this idea of self-play. So we bootstrap the weak agent into a stronger agent and then have the stronger agent play against itself. So to be clear about what this means, it means for the first move, we simulate the weak agent against itself loads of times. We find the best move, we play that. Then we simulate the weak agent playing against itself loads of times from that move, find the best move there, and play that. And so this is like really expensive, but the plays you get are going to be better than the weak agent could have come up with on its own. And you now have a lot of data points of the form, in this state of the board, play this move. And these are kind of smarter moves than the weak agent would make itself. And you can now retrain the weak agent to play these moves. To tell it, hey, the stronger agent took this move, took move 1, but you'd normally take move 2. You should be a bit more likely to take move 1 next time. You just like do this back and forth lots of times, and like this is the core of how AlphaZero works. And I think it'd be reasonable at this point to be like, what the f? How did that work? And so I think that I think this is like pretty subtle, but the ocean crossing point here, the like step where this problem went from unsolved to solved, is so we always know that we can spend more compute to perform better. You can like run an algorithm for longer, get more samples from distribution, and like learn it a bit better. The key is that we can then approximate this more compute with less compute. And this is the power of neural networks. They can take a really expensive complex function and learn how to approximate it well in a fairly cheap way. Like, you can train a neural network to distinguish between pictures of cats and dogs. This is a hard problem, but you just tell the neural network, but actually running the network is pretty cheap. And it's learned how to approximate this really complex function of just actually understanding cats and dogs. And this is even more awesome because we're doing this recursively. We're taking this like compressed compute down into this cheap neural network. We're then scaling up the neural network, and we're then compressing it down again. Like a picture I find it useful to have in my head is we're like trying to explore a tree, and we learn how to summarize like these, looking like one step further into just like a single node. And now when we do it again, we've learned how to compress 9 nodes into 1. Then when we do this up again, we've learned how to compress 27 nodes into 1. And that like, because neural networks are awesome, and because we can just keep doing this, if we do this enough times in this horrifically expensive way, we can learn how to approximate. We can like create knowledge from nothing and just be incredibly powerful. Another intuition you might have for like how any knowledge emerges from this is that if you're kind of in the end game, this approach works pretty well. Like if you're 3 moves from winning, it's not that hard to learn what those 3 moves look like. Which means that if you've learned that, then if you're 4 moves from winning, it's not that hard to learn it's not that hard to learn how to win. If you're 5 moves and you've learned how 4 move works, it's not that hard to learn how to win. And so kind of analogous to Q learning in dynamic programming, it's slowly learning backwards. And yeah, one of the really interesting things about this is the way computer, say, chess programs normally work is that they try to evaluate the worth of a position. But things like, how many pieces do I have? What's my positional advantage? Are my pieces free? Stuff like that. And this is completely different. This is saying, when I played this game in the past, how many times did I win? And this is a lot more analogous to the human intuition of when I look at a state, how happy do I feel about the state? How likely do I think I am to win in this state? Like this is just like a complete paradigm shift in how computer gameplay works. There are some further details that I don't think are interesting enough to go into. This has a bunch of limitations, like it's a perfect information game. There's a symmetry with your opponent, so you can do self-play, which you wouldn't normally be able to do, which you wouldn't be able to do in like a more complex problem. And this means that you completely resolve the multi-agent problem where you're like smarter than your opponent, or your opponent's smarter than you, because you're always perfectly balanced. But yeah, as I mentioned before, there was some impressive work with extending this. And yeah, that is how AlphaZero works. I hope that was a sufficiently cool algorithm. It would be sad to end the talk without having talked about it. Thanks everyone for coming. I think I'll end there.
Thanks a lot for another sequence of great talks and for some good life advice as well this time. Yes, thank you to everyone for coming. And yeah, I'll say this to the few people who are still here, that so this long summer finally looks like it's coming to an end, which means for the time being, this will be the last in our series of student talks, and we're going back to our classical term time talks, which will still not be very classical. They'll be on Zoom, but yes, we're going back to term time talks, starting in 2 weeks' time, and we have a lineup which I'm personally quite excited about, so it'll be nice to see loads of people there. It should be good. So yeah,
yeah, thanks everyone for coming.
And safe travel to everyone who's going back to Cambridge in the following week or so, and good luck with whatever you're exploring next to people who are not.